Okay, what we have seen in the previous class is this a1 1 c1 and so on to a1 n plus 1 cn plus 1. Same way an1 c1 and so on to an n plus 1 cn plus 1. So there are n equations. Okay, there are n equations here because c1 and so on, that is a1 a2 and so on to an. Therefore n equation. How many unknowns? c1 c2 cn plus 1. So there are n equations. Okay, there are n equations and n plus 1 unknowns. It is also homogeneous equation. Okay, the last equation is a system. The last homogeneous system has fewer equations. Few equations are there because we need n plus 1, but there are only n equations. That is why we call it as fewer equations than unknowns. Okay, how many unknowns are there? N plus 1 unknowns, and there are only how many equations? N equations. There are only n equations. From n equations, how we can find n plus 1? So one can be written in terms of the other. Okay, any one term can be written as c1 can be written as all the equations can be written in terms of c1, or all the equations can be written in terms of c2, like that. So there exists a non-trivial solution for c1 c2 and so on to cn plus 1. Means c1 can be written, for example, all c2 c3 c2 c3 and so on to cn plus 1 can be written in terms of c1. Okay, so this is not the non-trivial solution. Okay, this means that T is linearly dependent. If it is linearly independent, what will happen? C1, C2, C3, if it is linearly independent. Okay, if it is linearly independent, then what will happen? C1 equal to C2 equal to and so on equal to Cn plus 1 equal to 0. So each and everything should be 0. Then only it is linearly independent. Okay, if it is linearly independent, then C1, C2, C3 and so on to Cn plus 1 should be equal to 0. Each and everything should be equal to 0. Then only you can call it as linearly independent. But here it is having a solution. Okay, that is C2, C3 and so Cn plus 1 can be written as in terms of C1. So it is not equal to 0. That is why we have written it, therefore we have written it as linearly dependent. Okay, now B part is which implies T is T which contains n plus 1 vectors. So T is not a basis. Okay, T is not a basis for V. Now we have to show the B1. Now we have taken n plus 1 vectors, no? Now we have to take one lesser, n minus 1 vectors. Suppose T dash contains n minus 1 vectors and spans V. Okay, suppose you are taking the contradiction. It is having n minus 1 and it is also spans V. Okay, then we're taking the contradiction. Okay, it should not span V. We are taking the contradiction. That is, if it is having n minus 1 vector, it spans V. If it is spans V, then what will happen? Then by definition 1, okay, T must contain, okay, a basis, okay, B for B, okay, if B contains R vectors. What you are writing is n minus 1 vectors are there in T and it is spans V. We are taking the contradiction, it spans V. But what is the definition 1 says? Here we are having definition 1, right? What is the definition 1? Yes, here is our definition. Any finitely generated vector space generated by a set of non-zero vectors has a basis. Okay, it is finitely generated, means span. If S spans V, then it should contain a subset. Okay, and that should be a basis. So the subset of V1, V2, and so on to Vn is a basis. If it is V1, V2, and so on to Vn, spans V. So using this condition, we are sure that it contains a subset B and this is a basis for our V. Okay, a subset means the elements are less, no? So B contains R vectors. Suppose we are assuming that B is having R vectors. So we must have, okay, B is having how many vectors? R vectors. Okay, we must have R is lesser than or equal to, it is a subset, no? So you are taking a set which is having n minus 1 vectors, whose subset, how many elements will be there? It will be same number of elements. The set itself is a subset for itself, or some number which is lesser than n minus 1. Okay? Since B is a basis, now we'll take the help of A, right? Our theorem A part. Since B is the basis and S has R minus 1, okay, R minus 1, R plus 1, maybe greater than R, no? So R plus 1 or more vectors in it. Okay? It follows from A. What is our A part says? We are having here, what we are saying is a basis is there, that name is B, and yes, our set S has R plus 1. Our has, just now we have taken a set S. What is a set S? V1, V2, and so on to Vn. Okay, set has this basis, this R can be, R is lesser than n minus 1, no? Or it may be equal to n minus 1. Okay, so a set is having, S is having R plus 1 or more vectors in it. It follows from A. What is our part A? Part A clearly says that S is linearly dependent. If it is more R plus 1 vectors, no? Plus 1 you are having, no? Which is more vectors, then it should be linearly dependent. So this is our part A. From part A, okay, S is linearly, this is the contradiction, right? Linearly dependent. What is our S? S is the basis, and we are telling S is linearly dependent. A basis cannot be linearly dependent. The first condition of basis is it should be linearly independent. We are getting a contradiction that S is linearly dependent. So, this contradicts the fact that S is a basis, right? That's it. Theorem over. Okay. Now we go to another definition. Using this theorem only, this definition came into existence. Okay, very important definition. What we have told in this theorem is, if your basis is having n vectors, then if you take another set which is having n plus 1 vector, it cannot be a basis. If you take another set which is having n minus 1 vector, then also it cannot be a basis. So basis means it should have n vectors. Okay, a vector space V is finite dimensional if it has a finite basis. If it is having a finite basis, a vector space is having finite basis, then it is said to be finite dimensional. Okay, its dimension denoted by dimension of V, okay, is the number of elements. Okay, this is the important one, number of elements in the basis. So if the base is having 2 elements, then the dimension of that particular vector space is 2. If the basis is having 3 elements, then the dimension of that vector space is 3. So how many elements are there in basis? That gives you the dimension. Okay, if V does not have a finite basis, okay, if this V is not having a finite basis, then it is infinite dimensional. Okay, how many elements are there in the basis? That gives you the dimension of that particular vector space. If it is infinite elements are there, then we call it as infinite dimensional. Okay, that vector space is infinite dimensional. Okay, a vector space V is finite dimensional if it has a finite basis. Its dimension denoted by dim of V is the number of elements in the basis. How many elements are there in the basis? That gives you the dimension. If it is having infinite number of elements, it is said to be infinite dimensional. So R, the real number line. Okay, R is the number line, one dimensional. R2, you know, R2 the plane. Okay, 1001. Okay, 1001. So 2 elements are there. So 2 dimensional. R3, we take R3, 100, 010, 001. So 3 elements are there in the basis. The space is 3 dimensional. That's it. Finished.